Right, so we should start. Pretty much almost everybody in the room knows Francis. For those of you who do not, it's my pleasure to introduce Francis. Francis is a product of Cambridge, the essence of a Cambridge product. He was an undergraduate here in mathematics at Trinity. He did part 3 here in mathematics at Trinity, did a PhD here as well in mathematics, working with Ray Goldstein, and very nice work, theory and experiments. You didn't do experiments, but working on using a lot of experimental data. It was very nice. And he went away, very scary, in Australia for 2 years where he worked on biomechanics, and in particular, I remember you gave a talk here on the biomechanics of the knee. It was very interesting. He's back here as a junior research fellow at Trinity, and he just told me that this is his last year because he's moving to Oxford next year. So this is the last year of Francis. And today he's going to tell us about his recent work on geometry and active matter.
Very much, Eric. Yeah, I don't know what's going to be more scary, having moved across the world to Perth or moving over to Oxford. I'll find out. Who knows? If you never hear from me again, you know what's happened. Yeah, so this is a story all about how to try to do something useful with active matter. So we're probably all at least passingly familiar with active matter by now. It's in all the trendy journals. It's a nice buzzword. Essentially, if you have some big collection of things that can swim independently but interact with one another in interesting ways, then you end up with collective behavior. Now, active matter, you can't call it a new field anymore. It's been around for 20, 25 years, probably, with that name. And it's kind of going through a bit of a sort of an awkward teenage phase now. We know sort of roughly what the field looks like. We're very good at analysing systems of equations that describe active matter systems. But it's not the finished article. We don't quite know how to harness active matter to do useful things for us. And so the essence of the projects that I'm going to describe to you are all about how you can use geometry to control active matter and hopefully, in theory, do some kind of useful work with it. Now, the example I'm going to be using is autonomous microfluidic devices. If you can make a little microfluidic chamber just slightly clever, just slightly able to respond to what it's processing, then you can eliminate quite a lot of cumbersome sensory apparatus, computational apparatus in your cell processing setups or whatever you have going. So, start at the beginning. Here is some active matter. Kind of a very beautiful example of active matter. This is a suspension of some long, thin, rod-like bacteria. I think these ones are Bacillus subtilis. These guys are sort of 5 to 10 microns long, maybe nearly a micron wide, and they're long, thin rods. And what happens is that, I've got some rods around here. Here's 2 bacteria. If I have one here and I have another one near it, they collide with one another. If the suspension is very dense, like this, they'll locally align, either parallel or anti-parallel to one another. But these things are also swimming, as you can see. And when they swim, they induce a flow in the fluid around them, which makes them all interact with one another. And that destabilizes large-scale alignment. So you get these swirls and, dare I call them jets? I probably don't dare call them jets. This isn't real turbulence, but it's kind of called bacterial turbulence to give you the idea that there's lots of swirling going on. Now we know all about the statistics of the velocities that you see in these things, but directionally, as you can see, you lose correlation over some distance. So you couldn't use these as they are to do something like transport something reliably from A to B, say. They'll enhance the diffusion of something, but I couldn't say, bacteria, make me transport a colloid from here to over here, and they'll just do it. We don't know how to control it to get that to happen.
Are the guys at the boundary dead?
I think in this video, this is actually, it's kind of a droplet of bacteria. I'm looking at the edge here. So this is the sort of the meniscus. And so it's kind of, the whole colony is expanding, I think, and growing outwards. So if we could corral these things to do something reliable, like move a colloid, then that would be great. The problem with bacteria is that they're quite unreliable. Any experimentalist who has worked with them will tell you that sometimes they just don't want to behave. It's Monday, they don't want to move, they just sit there and let it swim. Even if you do exactly the same growth protocol, sometimes they're fickle. But thankfully what we do have are bio-inspired, semi-artificial realizations of active matter. This is a video from a pretty popular paper from a few years ago out of Zvonimir Dodgik's lab at Brandeis, which has spawned a whole realm of other studies using, it is microtubules and molecular motors and a depleting agent to push everything together. And the result is an active liquid crystal. You just flood this thing with ATP, off it goes. And so this is entirely controllable. There's a recipe, you follow the recipe, you don't have to grow things, you don't have to hope. Put it all together, it'll just work. So we have artificial active matter, and so if we could control it, maybe we could start to do fun things, like robotics, soft robotics. So you might have seen this, I think this was last year, a paper from Harvard about a little guy called the Octobot, which was a soft octopus robot that had the endearing characteristic that if you filled him up with some fuel, then he would raise 4 legs, and then raise the other 4 legs, and then raise the other 4 legs, and then raise the other 4 legs, and so on and so on, all powered by microfluidics. There's no circuitry, there's no motors, nothing at all. There's just something clever going on in this sort of microfluidic brain here. But still, what you have to do with this thing is you have to fill it up. At the beginning of the movie, you'll see the experimentalist fills this chamber here with a bunch of fuel. Still needs fuel. The advantage of active matter is that it doesn't need directed fuel delivery. You don't need a fuel chamber which it consumes. You just flood your environment with ATP for motors or oxygen for bacteria. And off it goes. So you're swapping the complexity of power delivery for complex interactions. Interactions, I claim, we can control. Terrifying slide. The route this talk is going to take is going through the notions of first, how can you use geometry to control active matter, to reduce the degrees of freedom in a predictable way. And then, once we can control it, we'll go down this arrow into what I call functionalization. Don't know if it's actually a word, but it gives you the point that how can we make active matter do useful things for us? How can we endow it with function? And so the projects I'm going to talk about sort of go down that arrow progressively. So this started off a few years ago motivated by a theoretical study about active matter confined in a circular domain. Started doing some experiments. So what you have here, this is a dense suspension of Bacillus subtilis confined in a little circular droplet. So what you do, or in this case what Hugo Villon did, who did his PhD at the same time as me, did lots of experiments, slaved away down in the lab while I processed data in my office. He made an emulsion of bacteria. So you don't want to use it to paint your walls. This is just lots of little dense droplets of bacteria suspended in oil. You then let those droplets sediment down and then squish them down with a cover slide on top and then place your camera down, looking down on top. And what you end up with are these kind of pancakes. So these droplets, they vary. This diameter here is between 20, 30, and 100 microns. And the thickness into the screen is roughly 15 microns, I think. And just for comparison, the length of the cells in these things, as I said at the start, is between 5 and 10 microns. So we're sort of talking maybe a low tens of cell lengths for your diameter, if that. So what happens is that if this thing is confined in a circular chamber of just the right diameter, then all the turbulence is quietened down. The boundary controls the interactions that destabilize this whole thing and turns it into just a steady single bacterial vortex. For either-handedness, we 50-50 clockwise, counterclockwise. And that happened for quite a range of diameters of confinement. Now, if that diameter of your circular confinement is too small, then you end up with something that's just kind of jammed. It's only a few cell lengths wide. You don't have a continuum suspension behavior in the whole thing, and it just kind of jams up. On the other hand, if the diameter of that confinement is too big, then the suspension doesn't feel the boundary. So you end up with turbulent behavior reappearing in the center. Right in the middle, if you have your confining diameter just right, you get a kind of Goldilocks region where everything is great and you get steady vortices forming and without any turbulence. So you've taken all these degrees of freedom of the swimming bacteria and reduced it down to just 1 degree of freedom, just one scalar, just the spin of the vortex, just with geometry. So if we can use geometry to create single vortices, can we make these single degrees of freedom interact with one another using more complex geometry? In particular, if we could use, if we could design geometry such that we have, we can make 2 vortices interact in kind of a narrow region here, just on the edge between them, would we get behavior that's like what happens when you have 2 interlocking cogs? You might expect you have 2 vortices coupled on a small zone near their edge, they're going to co-rotate with one another. And if you can do that, well, maybe you can do that. So, here we go. Here is the experiment that we devised. What you have here is a square lattice of circular chambers where each one of these circles is 50 microns in diameter. That's kind of the perfect diameter for sustaining a bacterial vortex. But what we also have is a small little interconnecting zone between the vortices. And the size of that gap, we varied that between different experiments. Reasoning that that is something to do with the strength of the coupling that you would have, hopefully, between neighboring vortices. So these kind of diamond shapes here, these are pillars coming out of the screen, these are cavities, and so this is something like, again, 15, 20 microns deep into the screen. And it's all made of PDMS. So you fill this thing with bacteria, it's full with really, really dense bacteria, about 40% volume fraction, I think. It's super dense. And cross your fingers, take a video, stare at the video, it's going to blur your eyes a bit. And particularly these 4, if you look at them, hooray, they're counter-rotating, as we'd hoped. You can see this for over most of the square neighbours, typically rotating in the opposite sense to one another. So this is, I've been calling these can't remember if I used the word spin yet, but I'm going to use it now. If you call this whole thing a bacterial spin, scalar degree of freedom, coupled together in a lattice with an anti-correlation between neighbours, perhaps you've created a bacterial analogue of the anti-ferromagnetic Ising model, so with infinite spin, because we have continuous degree of freedom in each vortex. So you can see this a bit better if you start doing PIV. Define a circular zone in each one of your vortices, do some PIV, compute the average angular momentum about the center of the cavity, and then color your grid green or purple of varying intensities to give you whether it's clockwise or anti-clockwise. So look at a movie like this, you've got a nice checkerboard, you've got that anti-ferromagnetic interaction that we were hoping for, like the network of coals. Okay, so now let's play with the interaction constant. Let's change the size of this interconnecting gap and see how much we can affect that correlation between neighbours. And that happened. Turns out that when you increase the size of the interconnecting gap, you induce a co-rotation with your neighbours. And that turns out to be a more common phenomenon than counter-rotation for the ranges of interconnecting gap that we were looking at. There's, ignore this red line, I don't know why that's there. These blue blobs, these are averages over lots of experiments, and on the vertical axis you've just got the average correlation between neighbouring, pairwise correlation between neighbouring spins. So as you vary the gap size, down here you've got anti-correlation, then you get to a critical size of that interconnection, and suddenly it flips into a ferromagnetic regime with positive correlation between neighbours.
Can you make the connection invariable to the bacteria? Just to the fluid can communicate but not the bacteria? Mm. Because they go from one chamber to the next, right? You can see them following the wall and...
Yeah, absolutely. That is a good question. Presumably, if you could get a fine enough resolution to put down lots of tiny pillars. Yes. But the problem we ran into with this is that actually, when you start to try and make gaps of smaller than sort of 3 or 4 microns, no, we didn't even, we couldn't make the mask sharp enough. So I guess if you had a much more expensive technique to make a mask, maybe you could do that. But yeah, so we think the reason why you get that ferromagnetic phase is all to do with how bacteria couple to the boundaries around here. So a side story for the circularly confined bacteria is that actually what happens at the edge basically dictates what happens in the whole suspension. They organize along the boundary to form some kind of edge current, if you want to use a physicsy phrase, and then that corrals everything else into motion. So what we suspect is going on here is that you have an edge current going around these pillars, and so what you actually have is, instead of a square lattice of spins, you have spinning bacterial vortices and then a spin around this pillar, and so you have kind of a union jack lattice with 2 competing interaction constants. And if you write down the mass of that, you get quite a sensitive dependence for the effective square lattice interaction constant, depending on the difference between the interactions.
And if the gap is too small, then this current around these islands is precluded.
Yeah, exactly. I mean, obviously, in the case where there's 0 gap, then they don't communicate. In the case where the gap is really small, yeah, they'll struggle to get through because they're finite size, and their length will be long relative to the gap. That's kind of that's an intriguing side story. The majority of this talk is about building coarse-grained models using geometry to reduce degrees of freedom and write down easy to understand semi-quantitative phenomenological models, depending on how good your fit is. So, I mentioned the Ising model, square grid of spins, which interact with their neighbours. Well, now we have a square grid of bacterial vortices, and so we can write down a bacterio-Ising model. In the absence of knowledge of more detailed dynamics, let's write down a pseudo-equilibrium model and see how far that goes. So at every vertex of our lattice, we've got some scalar spin. Some real valued number that tells you how fast that vortex is spinning and in which way it's going. So now what you want to do is write down your energy, quote unquote. Every time I say energy, imagine air quotes, because it's not really an energy. It's something that we're assuming is being minimized. So in the Ising model, your spins are just plus or minus 1, just integers. In this world, we've got a continuous spin. We can see that they rotate with different strengths of spin, but there's a preferred angular velocity, a preferred spin. So that means that each site will write down just a double-weld local energy with 2 preferred spins at the minimum, and then an energy barrier to flip between them. So in the limit of making your parameters go to infinity, you recover the Ising model, because these spins go down to infinity. So now we write down the energy of a configuration of this bacterial vortex lattice. So we've got one term that's just summing all the double weld potentials for every site in our lattice, just encoding the propensity of a bacterial vortex to spin one way or the other, and then onto that we add on a term that is the sum of pairwise interactions between neighbours. Just exactly as you would for the Ising model. The Ising model is just this term, because you don't need to constrain your spins. So this parameter here, this is the really important one. This is your interaction constant. It tells you the strength of how the vortices are communicating with one another, and the sign of it tells you whether it's co-rotation or counter-rotation between neighbours.
So you allow for different speeds here, or not?
Yeah, absolutely. So that's why,
unlike in this Ising model.
yeah, precisely. So that's why we introduce a real valued spin for each bacterial vortex, and then say that it obeys a double weld potential. So that means that energetically, these are the preferred spins in the absence of any other interactions.
So, other than simplicity, do you have any basis for saying that it's a two-spin or two-site interaction? Because if you think of the obstacle,
Yep.
when the gap's wide, there's a circulation round the obstacle,
Yep.
which is linking 4 spins, not 2.
Yep. Yes, you can write down a Union Jack lattice model with 2 interaction constants.
Yes.
And then you can reduce that model down to an effective square lattice model with an interaction constant that is one of those interactions minus something times the other interaction. So yes, in theory, we did do that. In practice, square lattices are easier to show on the screen. On top of this, we need some kind of dynamics. We've got videos, we can watch these things. And again, absent knowledge of higher correlations, the simplest dynamics you could write down would be just overdamped gradient descent. Just the Langevin equation, where every spin seeks to lower this configuration energy subject to being kicked around by some kind of white noise. Temperature, not real temperature, of course. Noise strength. And so then this Langevin equation For large times, you end up with a Boltzmann distribution for the spins of your bacterial vectors. So, it's a pseudo-equilibrium model. The actual distribution is almost certainly not Boltzmann, but maybe it looks Boltzmann enough for this to work. So indeed, what you can do if you take this model, even in all its glorious simplicity, and try to extract your interaction constant from all your experimental data, you end up really neatly capturing those two regimes. So here's that critical gap dividing the co-rotating and the counter-rotating regimes in your square lattice. And so in this range down here, our interaction constant is negative, meaning that they're anti-ferromagnetic, and above that, you end up with a positive interaction constant. So even with this simple model, you can extract meaningful interpretations of the basic constants.
What's red and blue?
Two different ways of extracting the interaction constant. Either you can take all your data over a long period of time and then just fit a two-dimensional histogram, or you can do, I think it was linear regression on your data points.
Shouldn't you have done this non-dimensionally? After all, the gap width is relative to the size of these cells, isn't it?
Yes. Well, what goes into determining what all these interaction constants actually mean is a very messy area. Sure, absolutely. I mean, you could say gap width in terms of cell lengths, but it's not clear that the cell length is the meaningful length scale here necessarily. It could be that it's the decay length of the swimming of a single bacterium, or of the flow around it, or something. I'm not sure. But in theory, yeah, you could divide it. In practice, all these experiments were done at the same phase of growth of all the bacteria, so they should have all had roughly the same length in every experiment.
You fit your A and B potential parameters.
Yep.
You pick them so that you get the least best agreement with the data in some sense, or
Yeah, so you can fit those simultaneously with fitting the interaction constant, and you get a meaningful. You get the energy barrier between flipping from one spin to the other. That barrier decreases as the gap size increases, and that's sort of effectively saying that as you have a bigger gap, there's less of a boundary confining your vortex, and so it gets weaker and less central to flipping. So now, that was spinning things round and round. Spinning things round and round isn't transporting things, just rotating something. That's not going to get us anywhere. If we want to move things from A to B, if we want to do autonomous microfluidics, then that means we need to move from circular confinement, which gave us vortices, to linear confinement, which should give you directed transport, either one direction or the other. What works for circles should work for channels, and indeed it does, is confirmed in various active matter experimental systems. So the one at the top, these guys here, that's bacteria. Find them in a narrow channel, they pick one direction or the other and swim that way. These are colloidal rollers that exploit an electric field to roll spontaneously. And these guys are a dense suspension of sperm cells that, again, put them in channel-like confinement, they pick one direction or the other and flow. So this is more along the lines of what we want to do. We want to move things from A to B. So now, if we want to do this for microfluidic networks, we need a simple coarse grain theory for how the active matter system will behave in a network-like environment. If I place it, if I have some kind of world that I can think of as lots of narrow channels, and I fill it with my active matter system, in this case, dense bacteria, how will it now flow in this network environment? So now what we have here is a non-trivial network-like environment where each one of these edges in my graph, think of that as being a narrow channel full of bacteria. And at each one of these nodes where these edges interact, these channels can exchange mass with one another. So we're going to write down, inspired by bacteria, a simple theory for how active matter should behave in this kind of network. So the first thing to do is to assign an arbitrary directionality to each edge. That just means that we know that positive flow is this way and negative flow is flow the other way. Now, each edge has some kind of net flux of the active suspension through it. I'm going to emphasize that we're thinking of every edge as being full of active matter, whether it's flowing or not, because we're assuming this is a very dense suspension that we're using. So we have some scalar for each edge. How much is it flowing along that edge? And the one constraint that we're going to impose, because this is dense, that it is essentially fluxes are balanced at each node here. What goes in must come out of every interaction node. So now, inspired by the bacteria, we'll write down a pseudo-equilibrium model, how you'd expect this system to behave. Again, when you have a narrow channel, there is a propensity for spontaneous flow in one direction or the other down that channel. So you apply a double weld potential governing the flow along that edge. And onto that, you just add on a term. All that's doing is imposing this incompressibility constraint at the vertices. Just a soft way of saying flow is balanced at each vertex. That was a slight misprint. It should be, that D should be there, but it doesn't matter. All this is saying is that so long as that interaction constant is big, flows are effectively balanced at every vertex. So what happens is you've now written down a system where the preferred states are as follows. Take your network. Now, assign loops of flow around it. Because I've got the balanced flow at every node. What's got to go in, it's got to come out. So I've got to write down loops of flow. But I can't have more than one unit of flow along an edge because the suspension can't sustain flow of that magnitude. So what we end up with is a system where either an edge is flowing or it's not, and everything has to look like loops. The result of this is that, for this simple example here, there are 6 ground states in physics language, minimal energy states, and they all look like that. They're systems with 4 edges flowing and 2 edges in a quiescent state or in some non-net flux state. They have the lowest energy. Hello?
Do you count the same with the arrows reversed as a separate density?
Yeah, absolutely. On top of this, there are 8 excited states. They're local minima of the energy, but they're not global minima, and they have 3 edges flowing. The more edges flowing, the lower the energy, the more dynamically preferable the state. So on top of this then, when you put on Langevin dynamics again, because we need dynamics, we can watch these things going, you end up with a system that does what we call stochastic cycle selection. It'll sit in one loop, flow loop state for some random amount of time before noise eventually kicks it into another loopy state in the network. And this continues over and over and over and over. And the different loops of flow that you get depend on the topology of the network in which you're doing this. How frequently states change also depends on the topology. So you can see it's a bit better if you plot a nice shiny chimograph of the flow along each one of the edges in this thing. You get these bands where flow isn't changing, it's just fluctuating around one state before noise then kicks it into another state, then kicks it into another state, and so on and so on. Okay, but we're still not doing anything useful with this. We've turned spinning things round and round to moving things around in big loops in a network. So the final piece of the puzzle, at least the pieces of the theoretical puzzle, is to start doing logic with these things. I propose just by adding a couple of extra components, you can design simple networks that, according to this active flow network theory, can obey simple logical rules. You can create gates. So now at the moment we've already got vertices and we've got edges. Now onto this we need inputs if we're going to do logic. So here's an input. Don't worry too much about the maths. All that's saying is that essentially it's an input. That's a node whose net flux we're able to control. There's some external bath of active matter, and we have a mechanism to be either injecting mass through that vertex or not. So we control that. If there's active matter being injected through that vertex, that's an input on. If there's not, that's an input off.
And you can't extract.
You can. That's the notion of outputs. At an output, we think of those as nodes whose net flux we do not control. They're not constrained to a incompressibility. They flow out back into our external active matter bath. If it is energetically preferable for mass to be flowing out of that output, then think of that as an output of 1. If there's not mass flowing out of the output of 0. And the final thing that you need is diode edges. You need one-way edges. Essentially, you're just placing those in front of outputs to stop matter spuriously flowing back in through your outputs. So those kinds of diode edges, they can be realized by geometrically patterning your channel. Have a little sort of sawtooth pattern along the edge that rectifies active matter flow. That's been seen for a variety of systems. So now, I claim that the ground states of this network realize simultaneously the operations of OR and AND. It's very exciting stuff. This is foundations of logic. And it works as follows. If both the inputs x and y, if they're both off, then there's no mass flowing into the system. But we're conserving mass at every vertex in between, so there's nothing flowing out of the system either. So both our outputs are off. Okay. Now, if I turn on x, there are two routes this flow can go. Either it can go along this top, or it can go along and out of the AND output. If it's going out of the OR output, that's got 1, 2, 3, 4 edges in our network flow. On the other hand, if it's going out of the AND output, that's got 1, 2, 3 edges flowing. 4 is greater than 3, at least last time I checked. And so that means that the state where we have flow going out of OR is preferable to the one where we have flow going out of AND, which means that the ground state is the one where 1 OR 0 is 1, and 1 AND 0 is 0. Correct. The same thing happens for Y. If I turn on Y, but X is off, it's preferable for the flow to go along here, because that's more edges flowing than going out of AND.
Sorry, why is it preferable to have more edges?
Because that's the premise of the active matter system, is that where it can, the suspension will flow. So you end up with a system that it dynamically prefers to be flowing as much as possible. So you can sort of equate that with having ground states that have lots of edges flowing.
If there is an open end in the bottom one, then it will directly flow to the bottom end, not really take this upper route, right?
Not necessarily clear. I mean, so it depends on what is actually microscopically going on if you have this kind of junction here. So we haven't incorporated any kind of geometry into that junction. If instead I'd drawn it as a Y shape with 120 degrees between each of the legs, then I'd contend it was less clear. And in fact, we've got tantalizing experimental evidence with sperm cells that this does indeed actually happen. It will typically adopt the longer flow path. It's sort of hot off the press work in progress, but it does seem to be a reliable principle. And so now when you turn on both of your inputs, X and Y, well, by mass conservation, we've got to have flow out of both of these edges to end up with 1 and 1 for both your outputs as well. So we've recreated basic logic of or and and. Thing is, this is, as I said, we're conserving flow at every vertex in between. This means we've written down a kind of conservative logic. The sum of the inputs equals the sum of the outputs. You can do classical logic conservatively. You can do it with billiard balls. There's a whole range of physics dealing with designing geometries that will do logic with rolling billiard balls. And that's conservative. The number of balls I roll in has got to equal the number of rolling out. Just means you have to think in a slightly different way. And in particular, that means for things like NOT gates, which are not naturally conservative. 0 input gives you a 1 output, and a 1 output gives you a 1 input gives you a 0 output. You have to, for gates like that, you sometimes need a power. So this is how you realize NOT in an active matter logic formulation. So here's your input, X, and here's the output that's not X. What you also need then is a power input that is always on, that delivers the power for not X to be 1 when X is 0. And you also need 2 outputs, 2 additional outputs whose value you just ignore. Because they're the ones down which X and the power get dumped when X is on and you want output off. So again, this realizes not there's slightly more machinery. So in reality, you want to think in slightly more parallel terms. You want to just chain together some NOT gates. The conservative logic can simultaneously realize lots of logical operations. The one final thing you can also do is you can use the steady flow characteristics of active matter to start creating little memory devices. So the set reset latch, the SR latch, is a classical device that you, in normal logic, you create with 4 NAND gates or 4 NOR gates connected up in a feedback, sort of feeding back into one another. That gets you a system where you can control the value of the output using a couple of buttons. So in an SR latch, you have 2 inputs. You have a S and an R, a set and a reset. And you have 1 output, which seems to be called Q. I don't know why it's called Q. Now, what happens when I press the set input, the output gets flipped to 1. And it stays at 1 even when I release set. And conversely, in an SR latch, when I press reset, the output flips to 0, and it stays there even if I release reset. So effectively, S and R are my buttons for saying set my memory bit to 1 and set my memory bit to 0. I can always read that. And you can realize that kind of behavior in an active matter logic system. In fact, without the complication of having lots of NAND or NOR gates interacting with one another, actually all you need is your set input, your reset input, and your output, and then just an additional power and an ignored output. And this network, I claim, realizes something very similar to the SR latch behavior. And the reason is because it's got 2 ground states. So when S and R are both off, when I'm not pressing any buttons, it's got 2 equally preferable ground states, one with an output of 1 and one with an output of 0. So what happens when I press my set button, suddenly the presence of 2 ground states gets killed off, and there's now only 1 ground state when set is on. So the system flips into that state. And that state is one such that when I release set, it is closer in configuration space to the ground state with the output of 1. So with high probability, it flips into that ground state. So essentially you use set to change the ground state there. And the same thing happens for pressing the reset button. I turn reset on, there's only 1 ground state, such that when I release it, the state that's closest in configuration space is the one with the output of 0. So between these 2 toggles, you can realize this 1-bit SR latch memory device. So when you implement this with a bunch of dynamics and a bit of noise, you can see this coming out in a fun little plot. So the vertical axis is the value of the output, and then these colored regions. Pink is when you're holding reset on, and blue is when you're holding set on. So the output's at 1, flibbles around. When I release reset, down the output goes to 0, stays there until I press set, stays at 1, and so on and so on. One deviation from classical behavior here is that it flips to down to an output of 0 when reset is released rather than when reset is pressed. It would be slightly more complex to realize the full behavior. You could do it, you just need slightly more stuff to conserve mass. Oh.
Do you have any dependence on how long you press the buttons as to the actual result you get? So I see that if you press S, then you basically jump up to 1 instantly. But suppose you press R and you very, very briefly, is there some sort of minimum time you need to sort of press R for the system to adjust?
The answer is yes, in theory. That will depend on how quickly your system's moving around in the gradient space. In this case, you don't have to press it for very long, because suddenly the other state is not a local minimum anymore. You're not sitting in any kind of bowl, you're immediately going to move away from it. So, I'm not claiming we should build computers out of active matter. Last time I checked, my computer is very good at being a computer without being full of bacteria.
It is full of bacteria.
Oh, yeah. I chucked it in a bath of acid in there, I think. What I'm proposing is that we can start moving into a world where we have sort of hybrid experimental devices. We don't always have to have some passive device, microfluidic device, lab on a chip, where it just does one task and we have it hooked up to lots of computers that just slightly change the inputs based on what some complicated sensor is reading. If you can just start thinking about microfluidic systems that have basic logical elements in them that can redirect flow depending on the output that they're currently realizing, you can create much more reliable systems, potentially, that can perform more complex tasks with less machinery attached to them. So more broadly, the message here is that geometry seems to be a pretty powerful tool for controlling the behavior of your active system, especially since now we have artificial realizations of active matter. And finally, I'll just acknowledge the rogues gallery of collaborators down the bottom here, in particular Hugo Violante, who I mentioned him in the beginning. He did any experiments on bacteria that you see throughout this talk. Thanks for your attention.
There were questions, but we have time for some more. Yes, Pierre?
I suppose if you started constructing more complicated networks of logical operations, then you might eventually hit lots of local minima you mentioned landscape. In which case the question might become, what true dynamic. I mean, if there are very few minima, then no matter what kind of dynamic logical equation you write down with respect to whatever coordinates, you will get to that local minimum. But if you have lots of local minima, it might start to matter what the correct coordinates are.
Well,
so I guess the question is, how can you know what the correct reaction coordinates are with respect to which you have a non-trivial system? I'm not sure my question makes very much sense.
well, I can offer you a comment in a related area. Constructing more and more complex logical operations is actually it's an interesting process with these things. So, in writing down an equilibrium model, you're assuming you're assuming an infinite propagation speed of information between far separated edges, in some sense. So in reality, when I change an input in my bacterial logic system, I expect that to take a while to cascade through the system. There's a finite swimming velocity of these things. So that means when I'm starting to design more complex operations, the states that I get might not always immediately transition to the global minima. So you have to think carefully about what you're doing and perhaps take a sort of a global perspective. Or machine learn everything. Let's just do like deep learning of it all.
Is there anything like analog of Ohm's law for these channels? Because it seems like an electric circuit, and something which relates the flux to the local difference of something along the ends.
For bacteria or active matter in general, good question. I don't know. I would imagine there will be some kind of relationship which will be not linear.
There's probably Kirchhoff's laws.
Yeah, I mean, Kirchhoff's law is just mass balance.
Yeah, you need something more.
You need more than that to say what the
It's a
flux
bit
should
like
be.
Ohm's law, because you have this principle that you actually want the maximum amount of flow, which is interesting. When I was, I'm now sound extremely old, when I was in high school, I unearthed this book about fluid logic, which came from the late 60s, at a time when no activity, but the idea of having fluid flow which had hysteretic behavior at Y junctions because the fluid is going to the right, going to the right, was actually in contention as an alternative to silicon technology, bizarrely. And so there was a big literature on that then. Now, obviously, you have a completely different principle of the stuff wants to flow here.
Yeah. So
there you're basically minimizing dissipation roughly. And here you have something opposite. But I just wondered whether actually there's some mapping from one case to the other.
Sure. I mean, I've pondered that same kind of notion if you have some kind of highly non-Newtonian fluid. Because if you have some network and you push in your non-Newtonian fluid, in those systems you'll still get some levels of flow. It's not going to perfectly quantize as it flows through. And the notion of the bacterial system is that that's kind of a stronger effect. In reality, I'm sure that wouldn't be exactly true. You'll have small amounts of flow on edges that are mathematically non-flowing, equivalent to when you're having non-Newtonian flow. But I guess that case is almost an inverse of this one, in that it's a shortest path going along the longest path.
Exactly.
Maybe there's some kind of duality.
Yeah,
I don't know.
I was wondering.
This seems more like a superconducting, because there's
Could take up this interesting idea. Does it go faster in wider tubes?
What happens as you increase the width of the tube is that it slows down on average eventually. There's sort of...
It becomes incoherent again, right?
Yeah, exactly. So when it's very, very narrow, it can't flow. Then it gets better and better at flowing, and then it gets worse and worse on average. You start getting wavy behavior, and then you end up with bidirectional flow.
So you showed this computation with the network, with the flipping of the flow. Did you think of realizing the experiment? Because it must not be...
We're trying.
Okay. And does it work?
We think so. We're trying with sperm cells.
This first part of your talk was Forgive me, I'm used to saying easing rather than easing, even though the second is.
So whatever you want. It's
Yeah.
one of my main collaborator, Jörn, is German, and so he pronounces it easing.
Yeah,
So I kind of
this is
picked that
correct,
up.
but it's a little hard to say. But anyway,
Wait, which one is correct? I'm confused.
easing is correct.
And apparently, it's hard to say. I don't find
But
it very convincing myself.
well, my question is,
I've just said the wrong thing for years, that's all.
can you do something with it in this case? Because, as you know, the easing model
Sorry.
is not solved in 3D. Is barely with difficulty solved in 2D. And it is used to calculate something, you know, magnetization or, I don't know, specific heat or something. And you have temperature here. So you wrote this out, but is there anything one can calculate?
Well, the networks that we're dealing with here are all pretty small. So we can solve them all just by brute force. So you can calculate whatever you want. Perhaps I'm not fully understanding the question.
Maybe the question was if there are any analogs of these thermodynamic quantities that you would calculate with an easing model that you could calculate here, if I understand the question.
Well, to put it differently, does temperature play a real role in this easing model?
Well, sure. I mean, that's the strength of fluctuations. How that relates to the microscopics is a very, as I mentioned during the talk, it's a very difficult question. The fluctuations are going to be a combination of the real temperature in the lab, the viscosity of the solvent, what phase of growth they're in, the swimming mechanism as well. There are lots of ingredients that go into these parameters that I brazenly called temperature, for example. And it's strength of fluctuations from many sources, probably.
Okay, I think maybe in the interest of time, I propose that we stop, and then you can come and ask a question to Francis. Is that okay for everybody? So let's thank our speaker.